data center market has changed a lot over the years. For me personally, it started in the late 90s when really this market kicked off for us. We were designing what they called telehouses or internet hotels at the time, basically the start of the co-location market, rushing around Europe. They were very different. They were new. The technology was really evolving. The loads were much lower. The application of them was very different. It was very much sort of off-prem office type facilities. So then the bubble burst in the year 2000. We'd been going full gas designing data centers all around Europe, very, very busy. But the problem was the market wasn't quite ready for them. So the investment was flying in, people were building, but the applications and really the world wasn't digitalized like it is now. So they weren't ready. So things stopped, and it stopped for a while. Then basically a few years went by, the world became digitalized. We all started using email much more. We started using mobile phones to access different facilities and services and so on. As we are now, we're a very digitalized society, and the data center market came flooding back. There was that phase in the middle really where cloud really took off. So the global giants like the Googles, the Microsoft, AWS, Oracles and so on all started rising up and becoming global giants. They started driving the industry and really driving colo as well. So the co-location market became massive off the back of the cloud market. So really we had 4 or 5 global customers driving everything, either directly or through the colo market. And it was the decade of cloud. Facilities then were medium type load densities. We started to see rack densities increasing beyond up to 1 kilowatt to 1 to 10 kilowatts, which seemed like a lot at the time. But it was a steady increase. We also saw different technologies evolving. What started off as chilled water cooling systems with localized CRAs became mass air-free cooling to take advantage of really the efficiencies to be gained by using outdoor air to cool the facility through heat exchangers and optimizers. That was the middle phase. And then all of a sudden, I think it was 2022 or 2023, not long ago now, when ChatGPT was launched onto the market. When that was launched, everything changed. It really kicked off the world of AI, and nobody really saw it coming. Things rapidly changed, load densities started to increase, and we were very much talking about kilowatts per rack rather than watts per square meter, or kilowatts per square meter. So we're into kilowatts per rack now. And within no time, we went from 10 kilowatts a rack to 30 to 50, then 130. And really the next steps are 230, which is Rubin, which comes out this year. And then in a year and a bit from then, we'll be at 600 kilowatts a rack, and beyond that we'll be at 1,000 plus, so megawatt racks. So things have changed enormously. The challenge is now all about dealing with densification of load, cooling, power problems, massive scaling and resource, all of those challenges that come with an industry that's suddenly back in high innovation and boom time. The reason people are talking about Rubin at the moment, and Rubin is the NVIDIA infrastructure, is because it's out now. When we first started talking about it at DCW and various other functions, it was coming. So we were talking about, are you ready for Rubin? It was Q3, and they've just started taking the first Rubin compute trays to some companies in Silicon Valley on the West Coast. So these are now rolling off the production line. So ready for Q3. The reason it's important to be talking about this is because they go from 130 kilowatts per rack at Grace Blackwell, GB200, GB300 to 230, and it sets the benchmark for that rapid increase to 600 beyond. So Rubin is going to be roughly a 230 kilowatt rack. It's going to be in the NVIDIA, I think it's the MGX 1.2 rack format. So people need to be ready for that. They need to understand the connectivity, how the power connects, how the resilience works from the power shelves, whether it's N+N, or in this case, they tend to be set up for a 3+1 or 4 to make 3, as some people call it, resilient power infrastructure. The cooling is very different. The cooling for these racks can now run at 45 degrees C water onto rack. It has specific certified types of fluids that you can pass through, and they're very sensitive to filtration and cleanliness of the water. So there are lots of different technologies coming along now. The legacy data centers won't necessarily be ready for that, and the rack refresh rate and the technology refresh rate is almost annual. So if you're not readying yourself for Vera Rubin, you may have a problem. And the next thing is, what about tomorrow? So you need to be talking about this stuff. So when we talk about what's changing for the market in the future, because we've just talked about Vera Rubin, which is this year, and that's already quite significant change, things are going to move on a lot from here. The next step is likely to be Rubin Ultra, and this is the NVIDIA equipment, and obviously the others will be doing something very similar with Meta and Google, AMD. They're all working on the next technology to solve the problems of huge densification of power within a single rack. So what's likely to come next is a DC direct current power solution for the data centers. We've been designing systems with alternating current 400 volt AC distribution solutions for quite a few years now. The next step to really cope with the densification, the problem of losses in conductors, the coordination of masses of copper busbars or cables within confined spaces, and the connectivity to racks, it's going to go DC. NVIDIA are aligning with an 800 volt to 0 DC solution, which means new technology, new skills, new safety aspects, new design considerations, lots of things that are new. Now, some people remember DC from previous years where it was used on a much smaller scale for the telecoms market and other industries. It's also being used heavily in the electric vehicle industry now. So there are skills within other industries that we can start to bring across to the data center industry maybe, which I think is an interesting way of solving some of the skills shortages, but I don't think they exist heavily within our industry at the moment. So we need to be getting ready for that. And you know, that's really what Red are trying to do. We're trying to look to the future, always one step ahead. Don't look to today or tomorrow, look beyond that, and we're readying ourselves. And we're bringing in those DC power electronics skills to help us design some of those future solutions. So the really exciting part about what's happening in the industry is we're shifting from being MEP infrastructure designers to we're moving much closer to the product, the compute, and we have to understand what goes on within the compute tray, within the rack, to understand how best to design the systems that service this equipment. We have to understand the business model behind it. We have to understand about AI, what it is, how it works, and what drives the business model. So, and that's a fundamental shift and a fundamental change. Cloud will still exist and cloud will still grow, and cloud is something that we're all quite familiar with now. But the idea of an AI facility, high performance compute, AI factory, whatever you want to call it, is it is coming from a different direction, and it's a different beast. An AI factory, pure AI factory, produces a product. It produces tokens, and those tokens are the currency of AI. They're what creates the product that we're starting to get used to using. So the whole model is about producing or designing and constructing a factory to produce tokens, and it's a very simple single product, the token. Therefore, you start to approach things from a different direction and a different way of thinking. In the past, we would design a cloud data center, and we would look at how many megawatts or megawatts of load they want that cloud data center to be constructed to. You'd then look at all the infrastructure around it, and you'd look at how much utility power you need to make sure that all of that infrastructure can operate all the time under any condition, under any failure scenario, and also under the worst design day, which might be 1 hour, the hottest hour in 20 years for that location. If you can't meet all those conditions, you failed on the scope and the brief. The new model for AI factories is all about the product, which is tokens, and you make as much product as you can whenever you can. Very different to the concept of cloud, where if you can't meet the 100% requirements under all conditions, you failed the brief. So with the AI factory, this now starts to create opportunities. It means we have more flexibility over our power, and the challenge becomes how much of your utility power can you divert to the GPUs to make tokens. In the past, we would lock away a chunk of that power, and that would be reserved for the infrastructure. Which means it's stranded for a lot of the time, because if you think about it, if we're designing a system, if the brief is the n equals 20 condition, which means the one peak hour in 20 years, you're locking power away for all of the time apart from that 1 hour, and you're not utilizing that power, which means you're wasting production capabilities of tokens. So with AI, we want to be diverting that power to the GPUs, not stranding it in cooling systems, for example, have electrical infrastructure that can use that power when it's not needed for other systems, divert it to the GPUs. You can maybe put more GPUs in, deploy more, and use it when it's available. So it's a very different concept. So flexibility is probably one of the biggest challenges for the industry at the moment. There are different segments of the industry. There are the neo clouds, who tend to be pure AI operating, so they have it probably the easiest ride in a way, because from a knowing what to build perspective, it's very clear. They're building an AI factory, fill it with GPUs, liquid cooled and so on, and it's a nice consistent approach that meets the model. You've then got the hyperscalers and the colo customers. Now, they have more of a challenge because they will have machine learning, AI facilities within their data centers. They'll also have the large cloud proportion. Now, for the colos in particular, they will kick off a project, create a brief, find a site, and then they may not know who their end customer will be at the point of commencement of design. So they have a really tough call as to knowing what to build and to how to align the infrastructure. Do they go cloud? Do they go full AI? Or really what they need is a flexible approach that gives them anything from full cloud to full AI to hybrid. So that's the challenge, and we've been looking at that because we appreciate that is the problem of the industry, and that's the majority of the industry really for us at the moment is colos, hyperscalers, and really that flexible approach. So we started looking at the cooling system, for example. The cooling is a particular problem because you're starting to see this divergence of design cooling temperatures within the data center. You've got the equipment that's cooled by air, and that's been pushing up cold aisle temperatures to around about kind of 27, 28 degrees C, up into the low 30s in some instances. And that needs to be cooled by chilled water that tends to be around the sort of low to mid 20s. So that's one scenario. The great news for the industry, for sustainability and efficiency, is that AI is optimized for warmer water temperatures. In certainly in the NVIDIA case, not all cases, but I think it's moving in that direction. So it will end up there. But NVIDIA require water at 45 degrees C onto their GPUs, which means the water entering the CDU can be 42 or 43 degrees C, probably 42. Which means you've got masses of free cooling. So you need to benefit from all that free cooling, whilst still being able to cool your air-cooled part of the facility at the lower chilled water temperatures, and build something that is flexible enough to cater for whatever you install. Now there's the challenge, because you don't know what you're going to install necessarily at the start of the project, and with the rate of change of technology, things might change as well. If you think about a typical design to construction and handover phase of a project, if it's 2 years, for example, which is pretty aggressive anyway, you've probably gone through 2 tech refreshes by that point. So you've got tech refreshing, and you've got knowing what you want to build. That's the challenge. So if you ask what the answer is to the problem we just talked about as knowing what to build, it really is building flexibility. If you're not convinced that you're going down a pure AI factory route, you need to build flexibility into your solution. It's not easy, but it can be done. we believe it can be done from a cooling perspective pretty efficiently, which doesn't involve overspend on the capex, but still gives you the ability to optimize in all areas, maximize the free cooling in the higher temperature water solutions, but still be able to cool the air side equipment. You know, I sort of look to other industries as to how they do it. Being a Formula One fan, I look at what the 2026 regs have done for Formula One, and they've got these cars now which are incredible. They have a problem because a racetrack requires them to be very fast on the straights, and then when they hit a tight bend, they need to be maximum downforce and stick to the road on the corners. A car cannot cope with both of those conditions, so they've created these modulating wings. The rear wing and the front wing both change position on the corner to give maximum downforce, and then they flip up again for the straight and they're fast again on the straight. So they're fully optimized for all conditions, and that's what we need to do for data centers. We need something that's fully optimized for all conditions and be flexible enough to cope with any racetrack. The biggest mistake operators could make right now, and I would hope nobody would do this, but would be to go down a technology like something like mass air free cooling, because it isn't going to give you any capability to liquid cool the GPUs. Okay, so that would be a big mistake. Another mistake would be failing to look very far ahead, and don't just look to today or tomorrow. As I said, you need to leapfrog tomorrow, go beyond that, because things are changing so quickly. Annual refresh, you know, 130, 230, 600, 1000. That's the sort of annual refreshes we're starting to see with kilowatts per rack. And to put it into perspective, I mean, a lot of the industry will understand this already, but 600 kilowatts in a rack is like standing in your airing cupboard with 600 bar heaters switched on. This is phenomenal types of energy, and you know, you've got to be designing the systems to cope with that. It's a very different thing. You can't do that with mass air free cooling, for example. It has to be liquid cooled, so you've got to look ahead. Going back to the AI model, it's all about converting your utility power into tokens. So one way of doing that is to reduce stranded power, which we kind of mentioned earlier, but the other thing to do is to reduce losses and create the most efficient solution you can. And we approach it by sort of layering up the levels of efficiency and looking at everything. So small efficiencies in each component within the system all start to build up to create an optimized system. As you do that, each of those savings become product making energy. Okay, and there's many ways of doing that. One example would be to challenge the industry. So the certified or commonly used liquid mix to be used in the GPU cooling at the moment is typically turning out to be PG25, which is propylene glycol at 25% volume. And they put that in, they mix that in with the water to control microbiological growth and keep the water in a certain condition, which is great. The only problem with that is propylene glycol, when you add that to water, it impacts on its thermal properties. It doesn't transfer as much heat away from the load as pure water. Now, accepting that you can't go with pure water, you need something, but propylene glycol is quite viscous and thick. So that means you're always pumping a more viscous, thick fluid around the system. And in the world of AI, everything's pumped around the GPUs. They're all liquid cooled, which we think is great, but don't forget there's this pumping energy continually 24/7 being spent. So the challenge with propylene glycol is that it's thick and it's viscous, which translates into pumping energy. And as we said, we want to save energy, optimize the system and send that energy to the GPUs. So we looked at ethylene glycol. We're all quite familiar with ethylene glycol in cooling systems in Europe. It's not very nice from a toxicity perspective. It's toxic to humans and to biological life. It's not favoured by the planners and the permitters and the environmental agencies for obvious reasons if it gets into the watercourse and so on. And we've had to deal with that in certain circumstances where we need it as an antifreeze in the Nordics, for example, in the cooling system. But this is inside the data center. The data center is quite a controlled, secure environment. So we're taking something inside the data center. Why not use ethylene glycol? It's thinner, it saves energy, it's readily available. It needs to be tested to be sure. It needs to be tested with cold plate technology, make sure there's no sort of reactions and so on. But it saves energy, and we're used to using it elsewhere. So, you know, by looking at that, it could save something. And when you start looking at that on every level and layering them up, you make a difference. So tokens being the new currency of AI, this comes back to the model, the new model, and really back to this necessity to convert as much of your utility power into the product of tokens. So tokens, my understanding of tokens and how they work with AI is that when we request something from the model, that request is broken down into tokens. Tokens are short pieces of text or parts of a word or a whole word. Think of them as Lego bricks that by themselves don't mean a lot, but when you put them together and create a model, it starts to make sense. That's what tokens are in AI. So you make a request, it breaks that request down into tokens, words or parts of words. Suddenly the GPUs kick in, massive parallel processing, thousands of cores per GPU. That's where all the energy gets consumed, and it processes the request and creates the response. That response is then tokens that are then aligned and formed. The Lego bricks are constructed into a meaningful model, and the response is given back to the user. So that's why tokens are so important, and that's why every watt needs to be converted into tokens as efficiently as possible, because that's your product. Energy is one of the big pieces that we didn't used to worry about quite as much in the past. We used to worry about energy efficiency because of the cost of power. The problem now is energy availability. We are out of power in many areas. So focusing on energy is important. Unlocking energy problems is important within grids, but the AI factory model does start to give some new opportunities as well. Rather than worrying about the grid being able to provide 100% of the required power 100% of the time, there are opportunities now to potentially take power supplies where you can have 100% of the power for maybe 99% of the time, or 95% of the time. But when there's a peak in use elsewhere, you might have to accept a bit of a drop-off. Now, ordinarily for a cloud computing facility, that would be a major problem, because you would start to switch off services, lose critical facilities. In an AI factory, you'd make fewer tokens. But what it does is it creates opportunity to utilize many more power supplies around the world that previously may not have been considered. Continuing on the topic of energy, one of the other big challenges that we're having to deal with now is that the AI data centers at the enormous scale they are, and the scale now is, these are gigawatt plus, so thousands of megawatts. We're seeing, there's talk of 10 gigawatt plus AI factories in the US. We're certainly seeing 4 or 5 gigawatt facilities in the Middle East and several gigawatt facilities in Europe now being conceived. The issue with that is at that scale, with some of the power characteristics of the AI factory, it's starting to cause quite a concern to the power grids with power characteristics and harmonics and AI load characteristics, which can spike above your sort of design capacity. So it's starting to bring in new technology there that wasn't as critical previously, and battery energy storage systems are now becoming part of the solution. We're looking at things like supercapacitors at rack level to smooth out spikes at rack level, and large-scale battery energy storage solutions upstream of the data center to act as a buffer between the spikes from the data center and the grid, and also to possibly backfeed the grid when it's required, and act as a kind of a prosumer and a consumer to solve some of those issues. When you ask what comes next with an AI facility, I would say let's look at what the what the data centers have looked like, and the familiar data center up till now, and notice what's happening really to them. We've always called them data centers, buildings, warehouses full of computers that we walk around, and we walk between the racks and we look at the facilities from inside. They're getting smaller and smaller and smaller and more compressed, and I would say they're tending towards becoming more of a machine, a high density compute machine, very specialized, very dense and condensed, different types of infrastructure and services. When we talk about direct current 800 volt power supplies, and the industry needs to kind of catch up with that. So it's not necessarily a friendly building that you walk around. It's a very specialist piece of equipment, and it's a different way of looking at it. So data centers are evolving into, in my opinion, into a machine, and they need to be approached and treated like that for the future. I think design principles to focus on are really engineering technology of the future. So what can we see coming down the line? Open your mind, don't be constrained. For example, one of the things that our R&D team have been looking at quite a lot recently is the idea of superconducting cable technology. And you know, it's really different. It's incredible technology. It benefits from superconductivity of materials. They're cooled. It's called high temperature superconducting cables, but actually high temperature in this case is minus 200 degrees C. It's got liquid nitrogen pumped around a core within the cable, and at that temperature the materials start to superconduct. The atoms within the materials stop vibrating and create a nice smooth path for the electrons to flow. So you end up with power carrying conductors that have no losses or near zero losses. It's new, it's quite expensive at the moment, but it's the sort of technology that could solve some of the problems of the future that we're starting to see. The idea being that, you know, a direct comparison could be 11 large bus bars carrying current to the load, being replaced with 2 sort of 100 mil superconducting cables. They make a massive difference. You know, it also could mean that we could start thinking about locating some of our power infrastructure maybe slightly remotely from the AI factory, giving you more flexibility over land packets and site locations. It could mean that you move all of your generator power away from the facility, away from the cooling, so that you don't have issues with re-entrainment from generators to cooling and cooling to generators and so on. It gives you flexibility, but it's new tech. It's the kind of stuff we need to be looking ahead again. One of the biggest challenges we face at the moment, aside from solving the technological problems of this rapid change, is the construction issue. You know, we have very long lead order times for generators, transformers, cooling. All the plant and equipment is on very long lead, and we also have a problem with getting these AI factories or data centers built quick enough. So it's all about speed to market. So the key is to find ways to speed up the construction. So speeding things up by standardizing solutions. The more standardized it can be, the more modular it can be. Off-site manufacturing, pre-manufacturing components so that they're kind of ready to be slotted into place with a new design that comes along. Really looking at modern methods of construction. Just to give a practical example of the difference between the old model and the new model, if we took a gigawatt utility power supply and approached it from a cloud data center perspective, we'd be looking at what our peak PUE or our peak power consumption on the design day would be. That might result from our 1 gigawatt utility power in about 650 to 700 megawatts of IT yield. When you switch to the AI factory approach and you accept that you're going to use that stranded power when it's available, for the life of your building, the majority of the time you can get an IT yield of over 900 megawatts. So you've really unlocked a few hundred megawatts of IT yield by switching to the new model, and you've utilized that power much more effectively. the message from us is that it's not just about are you ready for Rubin. That's an example to get us thinking and looking to the future. The real message is look far ahead, get ready for the future, embrace it, and be bold and brave with ideas.